Hello, hello. Our next speaker is Sebastian Faust. He is a professor at the Technical University of Darmstadt doing research on blockchain and cryptography. His talk is going to introduce the concept of generalized channels for proof-of-work-based blockchains. Generalized channels allow for any functionality to be available on layer 1 to be lifted to the second layer, which means that transactions can be both carried out instantaneously and at low cost, greatly extending the functionality of layer 2s. Let's give a round of applause for Sebastian.
Okay, good. Then, thanks a lot for the introduction. Actually, I have another slide about introduction of myself and my group. So we are a research group in Technical University in Darmstadt. We do research mainly on applied cryptography and also some blockchain stuff. For example, we did some research on proof of space, which maybe some of you have heard about. And we did a lot of research also on wallets, so how to secure cryptographic wallets, threshold cryptography, and in particular, which I will talk today about, is these second layer protocols. Okay, so we did some research in particular on virtual channels. This is something which we invented in 2018, first for Ethereum, and then later on, we also built this for Bitcoin. Of course, we do a lot of teaching. We have a big class in cybersecurity, which are around like 700 students. Usually, they don't like blockchain too much. They're usually skeptical, but yeah. Okay, so this was, yeah. And of course, we do some transfer. So we have a startup also, and they developed some stuff that we did in research. In particular, can I point here? Okay. In particular, this state channel network, which I also have this T-shirt here, PoW. PoW is was originally designed for Ethereum, but now it's also available on multiple other blockchains. And another thing that we also developed is Wildcard, which when the name somehow changed over the time. Originally it was called Erdstahl, and before this it was even called Komitee. It's some kind of scheme that allows you to execute smart contracts over arbitrary blockchains, but using trusted execution environment. Okay, so you can use a trusted execution environment, and then you can execute arbitrary smart contracts off-chain. So it's all about off-chain stuff. Okay, so I briefly go over this. So one of the main challenges, which you probably all have heard of is blockchain scalability, just to recall. So if Alice wants to send some coin to Bob, then she will do this over the blockchain, usually. And this is problematic because the blocks have fixed size and there is some time required to create new blocks. So in proof-of-work-based cryptocurrencies, you have to solve this expensive proof of work, and this takes some time. So this essentially means that we have limited throughput because, I mean, there's only, each of these blocks has a limited size. All the transactions, they have to be stored on this block, and we only create a limited number of transactions or a limited number of blocks per, let's say, hour. Then there's a limited throughput. And because there's limited throughput and there's high demand on the blockchain for transactions, and the demand is increasing over time, we have this results in high transaction fees. So okay, so Bob and Alice, when they want to make this payment, they have to pay a lot of money to carry out this transfer. So one idea, and this was, I think, originally invented already in 2013 or maybe even earlier, is to use some kind of what is called off-chain protocols. So where essentially you move these transactions to a second layer, so then also called second layer protocols, where you execute the transactions off-chain. So what did we do in particular when we looked into proof-of-work-based blockchains is essentially we had two constructions. These papers, I mean, in academia, you mainly care about publishing them at conferences, so we published them, I think, in AgioCrypt and S&P, so some conferences in security and cryptography. So this first paper was this generalized channels paper, where essentially what we do is we have this blockchain here, and this blockchain can be some, like Bitcoin. I think we tried it over Bitcoin, essentially. And Bitcoin has some scripts, right? So you can execute something more than just payments there, some conditional payments, for example. And you can do some OR conditions and AND conditions and things like this. And any application that can be executed on this layer 1, we can lift to layer 2. And this is what we call generalized channels. So it was kind of inspired by this notion of state channels that is popular, or at that point was popular in Ethereum, where you can like execute arbitrary EVM code on a state channel. And here it's the same like idea. So you have some logic that can be executed here, and you can lift it to this generalized channel and can execute it there. Additionally, this generalized channel has some additional other advantages. Okay, it's application agnostic, so you can run multiple applications in this generalized channel, off-chain, of course. So you can, I don't know, poker you can maybe not play, but something else which is supported by Bitcoin you can do. And it also offers interoperability, and moreover, it has some additional, if you compare it, I will actually compare it later with these Lightning channels. It has some additional advantages in terms of efficiency. So the on-chain costs and also the off-chain costs are reduced, at least for our measurements that we did, I think in 2020 and 2022. Okay, so then the second thing that I want to talk about it, which is kind of a very interesting concept, I think, is called virtual channels. So this is the basic idea is as follows. So you know, like in payment channels, you want to route transactions, or payment networks, you want to route transactions over multiple hubs, intermediaries, and they are connected by channels. So here Alice is connected with Ingrid via channel Alpha, and Ingrid is connected with Bob via channel Bob. And now one idea what they can do is, of course, they can route these payments over Ingrid. But what we kind of propose is this virtual channel is kind of a way to use the logic in these two channels to build another layer of channels on top of this. Okay, so, and then you can kind of cut off Ingrid. So you don't need to transfer, you don't need to route transactions anymore over Ingrid. It goes directly peer-to-peer to Bob. Okay, so they can communicate without Ingrid. So they cut again out the middleman. Okay, and I will explain a bit more how this works in a moment. So what is the advantage of this? It has high throughput and low latency. So because Ingrid is not anymore involved, she doesn't have to confirm each transaction, what she has to do in Lightning Network. So here it can be routed directly. It has low costs, depending on the use case, I think, because Ingrid doesn't take any fees. She, of course, will take some fees for allowing to open channel over her. Okay, so there's some fees involved, but at least you don't have to pay per payment anymore, fees. You only have to pay for opening the channel. And I think, which is nice, but nobody has actually really explored it yet, is that it gives you some privacy, okay? Because actually Ingrid doesn't know what kind of transactions are routed between Alice and Bob. She knows only that they communicate, or that they play maybe some game with each other, or they do some transfers, but she doesn't really know in which order they execute or things like this. Okay, so these are essentially the advantages of this approach. So then, most of you have heard about it. I mean, this also why I think essentially I got interested in this blockchain is that there's lots of security problems there, and that's why in cryptography, or that's why we essentially what we do is follow this approach of modern cryptography, which I want to briefly explain to you. Essentially, the idea is that when you design this kind of because these protocols are very complicated, so they're like usually pages long. Even like if you just give the pseudocode of this protocol, it takes a lot of space in the to describe this. But if you program it, it's even much more complicated. So what we do is to make at least the specification correct, we use this concept of provable security. Provable security essentially works as follows at a very high level. So first you have to define the security of your protocol, so you give a security definition. When you give the security definition, then you give a security protocol, so you specify what I said, like you specify how this protocol works. And then afterwards, you prove the security of this protocol. Okay, so usually there are some assumptions, maybe the signature scheme is secure, the hash functions are collision resistant and things like this. But given these assumptions, then you can prove the security of this protocol. And this has many benefits. First of all, it helps you to design good protocols without having any flaws in the specification. And then it also prevents ad hoc design. So these logos are from some famous attacks that were happening in SSL, so or TLS also, in some TLS versions. There are many design flaws where people tried to design these protocols ad hoc. They made many mistakes. And then it resulted into problems. And the same in the protocols, TLS and SL, I mean, they're complicated cryptographic protocols, but these virtual channel protocols are even much more complicated. So if you don't use like some sound approach for this, to protect or to make sure that you don't have design flaws, then you will end up with an insecure design. Okay, so let me briefly talk about this generalized channels. I will not explain in detail how this works because it uses some kind of cryptographic concept that's called adaptor signatures, which you also formalized in this paper. I can mention briefly what it is in a moment, but let's first look into this ledger payment channel. So these are the concept how this works. So you have Alice and Bob, ledger payment channel. They want to open a ledger payment channel between each other. They have like 4 phases, such a ledger payment channel. So there's a create phase, an update phase, a close phase, and a punish phase. Okay, so, and I want to briefly explain what happens in each of them. So in the create phase, Alice and Bob, they lock 10 coins on the blockchain, and then they can use this in the channel. So okay, so now they move these 10 coins each from the blockchain, but because they locked it into this channel, and now they can execute updates in this channel. So they can do updates and update the balance between each other. And how this is usually done? Well, there are like multiple different protocols, but in the very most simplest version, you can think of, I mean, they just sign this new states, okay? They have. But I mean, in blockchains like Bitcoin or so, where you have limited scripting capabilities, it's more complicated, and then you need something like the Lightning protocol for this. So you can update the state, essentially go like initially Alice owned 10 coins, Bob owned 10 coins, and now Bob transferred some 5 coins to Alice. So in this state, the state is now like this, that in this channel, Alice owns 15 coins and Bob owns 5 coins. And then you can continue like this. You can also, it's like a bidirectional channel, so you can transfer back and forth the coins. And at some point, you don't want to use this channel anymore, then you can go to the blockchain to close this channel with the latest state. The latest state in our case was this SN, where I think, maybe you see it here, where Alice owned 18 coins and Bob owned 2 coins. Okay, so then the channel is closed, and now originally we had like Alice owned 10 coins, Bob owned 10 coins, and now after this closing, Alice owns 18 coins and Bob owns 2 coins. So now, of course, the last important thing is now what happens if somebody cheats, because everybody has this, also in particular had these previous states, right? So this may be S2. And now Bob can say, okay, I don't want to lose a lot of money, and I just close the channel with a prior state. Okay, so not with the latest state, but with the state before. So Bob goes to the blockchain and sends actually the transaction that, or the off-chain transactions that he has, this SN-1 to the blockchain. In this transaction, he only lost 5 coins and not 8 coins. So he tries to close it with this. Okay, so in this case, the last transaction was 18.2, but now he tries to close it with 15.5. And in this case, what Alice can do, she can actually punish now Bob and receive all coins. Okay, so if Bob tries to do something like this, then there's a mechanism in these payment channels that allows to close this channel in such a way that essentially the entire value of the channel goes to Alice. Okay, so this high level how it works. So in Lightning channels, this is some implement. I mean, this was kind of the functionality, right? So what I just explained. And now how this is instantiated without going much into details how it works. But there's a funding transaction where Alice and Bob use some multisig, where they create this funding transaction. And now they have control over this with 20 coins. And then there are these kind of commit transactions where they say, okay, here in this original situation, 10 coins. This is actually a transaction that is on the blockchain committed. So you have like 20 coins committed on the blockchain. And now you create like commit transactions. And these commit transactions, they describe how these coins are to who they belong currently in the channel. So for the update, you do this kind of new commit transactions. But you see here these lines, these dashed lines, they mean that they're off-chain. So they're not yet on the blockchain. Okay, so, and in this original case, because Alice and Bob each funded this channel, 10 coins goes to Alice. Okay, this is the payout, and 10 coins goes to Bob. The same will be here on the other side, because both of them have such a commit transaction, because both of them should be able later on to close this channel. And then we have this punish transaction. Well, I don't explain exactly how it works, but essentially these are the coins the payout that is going to happen if you do a punishment. And in this case, if Alice publishes this transaction, so you can think of this like this, if Alice publishes this transaction illegally, then there is some way for Bob to extract these 20 coins. Okay, so this is basically the idea, and the same you have here. So here you have the same situation with the payment. 10 goes to Alice, 10 goes to Bob. But here there is this punishment for Alice, so that Alice can actually punish Bob. If Bob publishes this transaction illegally, then she can punish it, and Alice gets the coins. And there's this thing here, this x1 and y1, and these are some part of some hash time-locked transaction or premages, and they are like exchanged. So these are like random values, x1 and y1. They exchange between the parties, and later on, when you do a new update, you exchange them, and then if Alice or Bob tries to publish this particular commit transaction, then they can punish it. Okay, so you don't need to understand exactly how it works, but in a very high level, this is how it works. The scheme requires, in Lightning, requires that you have like time locks and hash locks on the blockchain. So this is some kind of features that you need on the blockchain so that you can actually do this, you can implement this. At least the basic specification of Lightning, it doesn't support apps, so you cannot run some more complicated applications there except payments. And it has relatively costly off-chain and on-chain communication. So on-chain communication, because well, if you do like some more complicated transactions here, then there's this punishment mechanism, and this punishment mechanism is relatively costly on the blockchain. Okay, so and then the off-chain communication, why is it high? Because you have these two commit transactions. Okay, and these are the things that we avoid in our design. So in generalized channels, this graph looks like this. Okay, so you have a commit transaction, only one, and then you have like the split transaction that allows you to execute apps inside this channel. Okay, so the high level works like this. So then you can run arbitrary apps off-chain. We don't require any hash time locked anymore, any hash time locked transactions anymore. We require time locks, but no hash locks. So you can run this over transactions, over blockchains that only support time locks and signatures. Okay, so you don't need any more than this. So you don't need, in particular, hash locks. Like in Bitcoin, you have it, but I think in Zcash, for example, you don't have hash locks, at least in this version that we looked into that time. You only have time locks there, but no hash locks, so you can actually run our generalized channels over Zcash. Okay, so. And it has reduced on-chain and off-chain costs because of the fact that we have only one commit transaction, and this punishment mechanism works in a more clever way. Okay, and how does this work? Okay, the protocol itself is more complicated, and in particular, what we use there is something called adapter signatures, and adapter signatures are essentially a way to realize hash lock transactions with signatures. Okay, so you can build adapter signatures. It was actually, I think, introduced by Polestra or so, yeah. So he introduced this concept, and then several people used it for different things, and people also constructed adapter signatures, I think originally from ECDSA, I think, and later it was constructed from Schnorr signatures, but there was no formalization for this. Okay, and in this paper, what we did, besides presenting this concept of generalized channels, we also give the first formal definitions of adapter signatures, and then we give like security proofs of the constructions that people have proposed. And then we show how to use adapter signatures essentially to replace the hash locks. Okay, so one application of this generalized channel, so actually in the beginning we started to work, we wanted actually, because we came from this virtual channel domain, and we wanted to build virtual channel for Bitcoin, but it turned out to be complicated. So we first had to build these generalized channels because they had to have some advantages. And then we built these virtual channels on top of it. So what is a virtual channel? So recall, this is the kind of setting that you have in Lightning. So there's this people, I mean, in Lightning they don't use generalized channels, but I'm using this now because I will talk about virtual channels. But so you have essentially these people, they are connected. Alice is connected with Ingrid via a channel, Ingrid with Bob via a channel. We call this typically ledger channels in our paper. And what they can do is, if Alice wants now to send 5 coins to Bob, then she can route this 5 coins through Ingrid. So okay, she sends this kind of 5 coins first to Ingrid, and then Ingrid has to further route it to Bob. Of course, Ingrid can cheat. I mean, she could just take the 5 coins to that she received here and not send it further, but then you have some nice techniques from the Lightning paper, essentially how to ensure that this is not gonna happen, that Ingrid cannot do this. This has the advantage that that is entirely off-chain. Okay, so all transactions now are off-chain. They don't need to, if Alice wants to send coins to Bob, she doesn't have to open a channel with Bob. She can do this by using this Ingrid. The downside, Ingrid has to be active, so she has to confirm every routing that goes over her, and there's no privacy. She sees, like, essentially what transactions are done through her, and she also receives money for each payment. So this idea that we had originally for Ethereum, but then later in Bitcoin, how we built it then for Bitcoin, is to kind of lift these channels to another second layer. Okay, so or third layer, I don't know. So essentially, what we use the blockchain. We use the ledger channels as a two-party blockchain. Okay, so essentially we allow these parties, they run a kind of a 3-party protocol, and then they open a channel, this virtual channel gamma, over these 2 ledger channels alpha and beta. And then the functionality of this virtual channel will be exactly the same as the functionality that was provided by the layer 1 channels or layer 2 channels, and this is then layer 3 channels. So they also have a create, they have an update, and they have a close. And the good thing is now this is entirely off-chain. So not only the updates or the payments are off-chain, but also the creation is happening off-chain of these virtual channels. The closing is happening off-chain in this channel. So everything is off-chain. Ingrid is not involved anymore in creation. Okay, she is involved in. She's only okay. So it's not anymore involved in the updates, but she is involved in creation and closing. Okay, for creation and closing, you have this 3-party protocol. But then for updates, it's like direct protocol, so I don't need to talk to each other. Or Ingrid doesn't need to confirm it. It's privacy preserving, and there's less fees. Okay, so how does this work at the high level?
Yeah. More privacy preserving, because in the regular model you would have more hops between than just Ingrid, which would help you to increase the privacy, similar to how Tor works, right? Whereas in the virtual channel it seems like Bob learns that Alice is actually paying him, which seems to be worse for privacy.
So I mean, like in this case, I mean, first of all, this goes further, right? You can do this recursively, so then it gets longer. I will talk about this later. But it's not only like 2 hops, but you can do this arbitrary many hops, and you can build like a. I mean, I'll show this in a second, but. So privacy preserving is, yeah, you're right. I mean, it gives some different type of privacy in the sense that you don't know what happens in this channel. Okay, so you know, anyway, you know that, I mean, Ingrid knows that they are somehow talking to each other to some extent. I mean, that they have like some payments to each other doing, probably, yeah, that there's some route between them. But she doesn't know exactly, I mean, like if maybe first Alice transfers coins to Bob and then Bob transfers coins back and so on. She doesn't know the payment flow, okay? So she only knows the beginning, how much money was locked in this channel, and she knows the end, what is transferred. But she doesn't know the flow, okay? So the flow is hidden. I think this is particularly interesting if you think about, I mean, if you think about app channels, okay? If you run some applications in there, then essentially you don't know what application they were executing, okay? If they were playing chess or poker or I don't know, whatever. But they only know that in the end, maybe Bob won 5 times, that he got the money, but they don't know how this happened. So if it wasn't just a payment or they played chess against each other, and Alice is just very bad in playing chess, okay? So her privacy is preserved in this case, okay? So this is the privacy. It's not like, I think also it's not perfect privacy, it's just like, we tried to model this somehow in the Universal Composability model, but we never managed to do it somehow because it was very complicated to even get it the right notion for this. Okay, so now how does this work? I kind of lost the time. I don't know how much time I have. Ah, there's this counter. Oh my God, 1 minute left. Okay, okay, so then let me just give you the high-level overview of this of this channel. Okay, so high-level, this works as this. So you have this. You have these 2 channels, generalized channels, alpha and beta, and they have this XA and XI in this channel. So this XA coins belong to Alice, XI coins belong to Ingrid, and here xi channels, xi coins belong to Ingrid, and xb coins belong to Bob. Okay, so now they want to create this, and what they do is they exchange in this channel. They exchange some open transactions. So they do. They both lock coins here. So Alice locks coins in this particular transactions C, and Ingrid as well. And on the other side, Bob and Ingrid as well do the same. And then once they have locked this, I mean, they have exchanged these transactions and signed them, then what they have essentially opened or created this virtual channel. So now this virtual channel has 2 C coins locked in total, where C coins belongs to Alice and C coins belong to Bob. Genau, that's exactly it. We had it before. I got more time. Now it's 2 minutes, no? Okay. Okay. Okay, sounds good. So I will continue talking then. So, okay, so then they can do updates. So the same as it was for ledger channels, so can exchange like signatures between each other and update the channel. So now in this case, 2C coin belong to Alice and 0 coin belong to Bob. And then they can also close it, which essentially means they kind of go back to the layer 2 channels, to these generalized channels, to the ledger channels, where they update the balance, okay? Because here in this case, Alice was the person who owned get some money. So she, in her channel with Ingrid, she gets C coins. Here, Ingrid loses coins because she has to pay Alice. So she has only now minus C coins. But Ingrid was just the intermediary, so she has to be compensated on the other side. So here she gets C coins from Bob, and Bob loses C coins from in this channel better. Okay, so essentially you can think about these virtual channels, about channels that have not been funded on the blockchain. So usually you have a funding transaction, but now we don't have a funding transaction. The funding transaction just happens in these generalized channels. Okay, so you have a funding essentially in the generalized channels, and then later on, what you can do is you can do some offloading. 30 seconds. Okay, I will go over this. It goes more technical. So I'll jump over this. Okay, so I will just briefly talk about this then, yeah? So, because this was also your question, okay? What you can do is actually apply this technique, what I explained, or like what I mentioned. You can do this recursively, okay? So you can essentially, you have to have this channel network. You can now build first a virtual channel between Alice and Bob, where Ingrid is the intermediary, but now you can use this because we designed these channels such that the API is exactly the same for this and this and this. It's all the same, the API. So you can now view this as the ledger channel and continue building stuff over it. Okay, so now I can build channel delta between Alice and Charlie, and then Ingrid and Bob don't have to be involved anymore in the execution. Okay, and you can also use this kind of technique, the same technique, to build in cross-chain channels. There are also some papers about this and also some implementations about this. Okay, so we implemented this. Also, the people from the Polycrypt implemented this. It's called PoW framework. Originally, it was implemented for EVM chains, so for Ethereum. But now there's a lot of other implementations for Dfinity, Stellar, HL, Hyperledger, Polkadot, Cardano, and Nervous. So you can also use this for PoW-based blockchains. So how much time do you have still? Or 0? Okay.
So I do want to give people, so there is an hour and a half lunch break. So we're back here at 2. If you want to keep asking questions.
Yes, okay, so maybe I'll stop here.
Stay behind, but I do want to be cognizant.
If you have some more questions,
of people's time. There's some restaurants downstairs. So I think 3 different options or other places around for food. Yeah.
Are there any questions? Yes? The fee model is a good question. Yeah. So I mean, like the fee model is like this, that you. I mean, in Lightning you pay essentially a base fee, and then you have like a fee for transactions that you route, right? So here it would be that I think the fee model would be different, because essentially what you would do is. I mean, you also will make a base fee because you open channel, but then additionally you will have a capital cost, because Ingrid has to lock money, right, for some time. I mean, she locks. This was what I had here on the slide, right? Oops, no, yeah, okay, it goes back. This was this thing what I had here, right? When you open this thing, you open this channel. So when you open this channel, right here you have locked Alice, no, Ingrid. She's not really actively involved in it, but she has to lock money. So she locks C coins in this channel and C coins in this channel. So for this lock capital, which you can then use, because you can also, like, of course, join this together with, you can combine it with this hop-based routing that you use in Lightning. Then she has less money for doing normal routing, okay, because she has locked these C coins there. So she will ask for some money depending on how much money she has locked and for how much time. So I think we thought about what kind of application. I think if you just do payment to you and then next second I do payment to you and then next payment to you, then these virtual channels, they don't make much sense as application. But I think they make mainly sense if you do lots of payment to one party. For example, assume that you pay for Wi-Fi. Yeah? Okay, so then each megabit, or I don't know, like each kilobit that I buy from you, I pay for it. So then I do lots of payments in one direction. So then it makes some sense to open this. Yeah? Or I think in general, it's good for applications. So if you want to do some game in it and you pay for, I don't know, or you might run multiple games in it, and each game in this channel is some step, then you can do this probably also over, I mean, this will be very difficult to do this over like hopping stuff, because she can like abort, like, I don't want to, so you want to that your channel lives as long as you're playing this game. So there it makes a sense, and then you would probably pay some fees for this application. So I think it's nice to combine both things. Your question? Or?
I think it's too specific for this audience. So
Okay. Some more questions or food?
Food.
Thanks.